I think we record, Sylvie. Is it a problem?
No, for me, no.
Okay. I think Walter is, okay. Okay. Welcome everyone to this installment of the non-commutative geometry seminar. And today is Sylvie Paycha. I'm particularly happy to introduce her from Berlin and a Galois group on meromorphic germs and locality evaluators. Please, Sylvie.
Thank you, Jenny. Thank you, Walter. Thank you to all the Richard, all the co-organizers of this very interesting seminar. So I'll first a disclaimer: I'm not a non-commutative person, and I have been very much influenced, I think, by the non-commutative tradition, non-commutative geometry tradition, and often find myself talking to people from this community, but I just want to warn you, it won't be about non-commutative geometry. Yet it is very much inspired by some work of Alain Cohn and together with Dirk Reimer on renormalization. And that's maybe where my link to this community lies. And it'll take another route, a little different from the very inspiring work by Alain and Dirk. And let me go into it slowly. So these word Galois group and locality I'll explain, as well as evaluators and meromorphic germs. And let me start with some motivation from physics. So I'm going back to some old stuff that you're probably familiar with, to some work by Eugen Speer, 1967. So there will be some small print. Don't worry too much. It's when there's small print is that it's not too important, and I'll read it out for you. So he looks at the perturbation series expansion in a Lagrangian field theory, and he considers a non-zero mass situation. And let me read out for you an excerpt of his article. In this paper, we apply a method of defining divergent quantities, which was originated by Rietz and has been used in various contexts by many authors. I leave out a part. We find it necessary to consider functions of several complex variables, Z1, Zk, one associated with each line of the Feynman graph. The main difficulty is the extension of the above, so Rietz's treatment of poles, to the more complicated singularities, which occur in several complex variables. So what does he show? That he shows that indeed assigning to each line of the graph a new complex, a different complex variable, Zi, he lands in a filtered algebra of meromorphic functions. He looks at functions. Later on, we'll focus on germs at 0 because we just want to focus on one pole. It'll be 0. But he looks at functions. And what do they look like? So the k is now fixed, so it would correspond to the number of lines in a Feynman diagram here. Do you see my mouse? Yes? Do you see my mouse?
Yes,
yes, it works.
Yes, we do. Yes, we do.
Good. Okay, so this is a function of Z1, Zk multiplied by this type of pole, which when you're familiar with computations of Feynman integrals come from gamma functions. What do they look like? They're just sums, partial sums of these zi's arising in the among the variables of this function. So just a product of linear combinations of the zi's, but only allowing as coefficients zeros and ones. So what does he do? He wants to evaluate such functions at 0. So I've translated everything he does to 0. He does it at 1, but that doesn't matter. At 0, when obviously if they have that kind of pole, you cannot directly evaluate them at 0. So he uses what he calls generalized evaluators. I'm not sure that's the first occurrence I saw of this terminology. Maybe you know of more of previous work which uses this terminology. What does he do? He takes a linear form because you want a number, you want to evaluate these meromorphic functions at zero, at their poles. So he takes linear forms on this type of algebra with some constraints. He wants them to be compatible with a filtration, namely when you reduce the number of variables, you just get the same as if you had started with this reduced number of variables. What's important for us is that they should extend the ordinary evaluation when you're evaluating holomorphic functions at zero, because otherwise the convergent case would be out of control. So you just want to, when anything converges, you want it to be evaluated in the same way as the usual way. A very important property that he requires is that if F1 and F2 depend on disjoint sets of variables, then the evaluator should factorize. So it should evaluate independently functions which we can view as independent insofar as they depend on independent sets of variables. This we should keep in mind. We'll call that partial multiplicativity. The two remaining requirements are put in small print because they won't be essential for us in some way. We'll see. Number 3 is the invariance and the permutations of the variables. Indeed, you wouldn't like your evaluator to depend on how you've numbered, how you've decorated your lines. And so this is what is required here, that it doesn't see the effect of a reparameterization of the variables. A very simple one, just shuffling of the variables. The fourth one is, so can you see the fourth one? Because right now I can't see it.
Yes.
Yes, good, very good. I can see things coming up and down from my screen. So the fourth one is a convergence requirement, which we'll leave out completely. We'll be focusing on algebraic properties rather than analytic properties for the moment, although, of course, analysis is there all the time because we're talking about meromorphicity. So it's a natural continuity condition, namely that if you have a family of these functions with the same poles, the poles don't change, then the resulting holomorphic function you have multiplying by these poles should converge. We'll leave this out completely. The third one will have, in fact, as an essential ingredient, but in another form. It's kind of a partial covariance property, this third one, because you don't want things to depend too much on the way you parameterize your edges. We will build in the covariance in the construction. Our construction will be completely covariant. So we will need this because it'll be built into the framework. Don't hesitate to ask me questions at any stage. Otherwise, I'll just go on if there are no questions right now. So I'll introduce the framework and the protagonists. So here is A. You can think of A as Feynman diagrams. I'll go into it later in more detail. Phi, you can think of them, phi as Feynman integrals, assigning to a Feynman diagram a meromorphic germ. First, they will be germs at zero. We focus on zero. The bullet here will tell us what type of germ. We just saw Feynman types, we call them. And then from there, we want to get a number. We don't really want to stay here. We really want to get a number. And this is where the evaluators come into play. So that's what Speer did. He introduced an evaluator with the resulting composition, evaluator composed with phi, giving you a measurement. Starting from a Feynman graph, it spits out a number. Now, what we will show somehow is that modulo a Galois group transformation, which I'll tell you about, we can do it directly this way, which amounts to what we will call, and I'll come back to this repeatedly, a multivariable minimal subtraction scheme. Namely, we're going to project in a very naive way, except that the sophistication lies in the fact that we have multiple variables, and then we'll evaluate. So let's go into that, and let me talk about the protagonists. So this will be an algebra, and this is a concatenation. So you can think of concatenation of graphs. This whole work, you saw two names in the first slide, Binjiang and Li Guo, who are with whom I've been working for decades now. With them, and together with Pierre Clavier, at some stages, in fact, our motivation didn't come from Feynman graphs, but from cones. I'll go back to this. And then with Pierre Clavier, from rooted trees. So you can also think of cones here, concatenation of cones, or polytopes you could also think, or concatenation of trees, which gives you forests. Okay, then M will somehow reflect what you started with. If you started with Feynman graphs, you might expect some type of meromorphic germs with some type of poles. If you start with rooted trees, you might expect another type of pole, or with cones, yet another type. And that's what the bullet will tell us about. And then phi will be a morphism from this algebra to these meromorphic germs. What can it be? Feynman integrals, it could be. If you have trees, they will be generalizations of multi-zeta functions, branched zeta functions. If you have cones, they will be conical zeta functions. Conical zeta functions. I won't go into this now because it would be leading us too far away. But in fact, this was our motivation, and our motivation came from an article by Berlin and Verne in equivariant geometry, who, wanting to compute the Todd function, or wanting to count the Todd function on a toric variety, found themselves, without really realizing, using a Birkhoff-Hopf factorization. So there was a hidden coproduct, and they were using a multivariable regularization, all that not in those words, of course. So it's in the tradition of Erhard polynomials, counting integers on cones and on polytopes. That's where we started from. Okay. Any questions? I'll come back to these notations. Do you have questions on the framework for the moment? Okay, so let me go on. So our main protagonists, as you might have seen, figured out, is the target algebra. And before we go too far, let me say that as from now, hoping you still see my mouse, we'll work as from here to the right-hand side. We'll forget about where they come from, just retaining from where they come from the type of poles we have. So it's an algebra of meromorphic germs at zero. If we take one variable, if we don't do what Speer did, nor what Berlin and Verne did, namely if we, as a physicist often does, use dimensional regularization in which you perturb the dimension by one parameter, and this perturbs everyone in the same way, you could say. So there's one parameter shared by everybody. Then you can't do what we did. You cannot use a minimal subtraction scheme because you quickly realize that doesn't respect locality. And this is how where we got some inspiration from Alain and Dirk's work using the algebraic Birkhoff factorization approach. But we will take a multivariable approach, which takes us along another route. So you see, we have a filtered algebra like Spear in several variables, and since the Feynman graphs can have as many edges as we want, the trees as many vertices as we want, the cones as many faces as we want, as many edges as we want, there's no restriction on the number of variables. We're going to work with a prescribed type of pole. Remember that Spear had these partial sums. Here we're just going to require linear poles. It might look restrictive, but I've never met anything else than linear poles in renormalization issues. If you have, I'd be very interested to see. So we'll be working with linear poles, and let's see what type of poles we come up with cones. So as I told you, this comes from looking at Laplace transforms on polyhedral cones motivated by algebraic geometry, namely toric varieties and flag structures, which I'm not competent in, but that's where it comes from. Wanting to count integer points on cones, and of course there are infinitely many integer points on a lattice intersected by a cone. Yet then when we look at the poles resulting from a Laplace transform, were it continuous or discrete? If you want to count integer points, you might want to take a discrete Laplace transform. If you want to compute a volume of a cone, you might want to take a continuous Laplace transform. In fact, that kind of conical poles, in the sense that they are relatively arbitrary. You see, you can have any type of linear combination. So these cones we started with are in fact host all the possible linear pole types of linear poles we have encountered since then. You see, the ones we had with Feynman graphs is just taking the A's, the coefficients 0 or 1, and that's what we'll denote by M Feynman. Chen integrals, which come up either in Kreimer's toy model with a tree, a forest or a tree description or tree-like approach of quantum field theory. Then what you have nested structures. You see, you see this xj1 appearing at the next stage. And so that's why it's called Chen, because it's like these nested integrals or sums that you find in Chen's original work. And this nestedness is reproduced, is reflected in the type of poles. So again, it's a specific instance of that and of this. So there's a hierarchy here. This contains that, contains this. Okay, and this, in fact, with Dominique Manchon, we started a long time ago, I don't know now how many years ago, working on multi-zeta functions, and we already saw those structures. That's maybe the starting point for me, at least. Okay, so, and then branch zeta functions, which are a bit more general, namely, you see, this is, if you think of multi-zeta functions, it's like a ladder tree, whereas here we'd have general trees and the poles are reflect the structure of the tree. So you follow the branches of the tree and you see what type of poles. Any question? Don't hesitate, please don't hesitate. So At the beginning of the talk, I mentioned partial multiplicativity. This is to respect kind of the essence of what I retain, at least, of locality principle. So this we developed with Binjang, Li Guo, and Pierre Clavier. This kind of algebraic interpretation of locality. A lot of the richness of locality is lost. It's just a principle that is algebraic principle that retains some aspects. So let's go back to what locality is. It says that an object is directly influenced only by its immediate surroundings, or two events separated in space can be measured independently. So some of you might say, oh, there's no space-time, no causality. I'd just like to point out that Kasha-Reisner transposed to a Minkowskian setup this notion of locality we developed and managed to fit it in with causality. Okay, so what does it say? It says that, remember there's algebra A, Feynman graphs, cones, trees. If in some way we can decide they're independent, then the measurement of that concatenation, I'm being very vague here, concatenation of graphs, of trees, of cones, factorizes. Remember, that was one of the requirements that we saw in another form in Spear's approach. So this is very vague, and now we want to make it a bit more precise. And for that, we're going to use a notion of locality, which will be a binary symmetric relation. We'll put a T, namely like a perp upside down, and it's not by chance. You can think of perp as being a typical locality relation. It separates two objects that are orthogonal to each other. Evaluator will be so we'll transpose Spear's generalized evaluators to locality evaluators. And what should they do? Remember, Spear had, these functions should be independent where they don't depend on the same, when they depend on disjoint sets of variables. We'll replace that by an abstract notion of independence, and we'll say the evaluators have to factorize. Our claim is that on certain algebras and meromorphic germs with a prescribed type of pole, in general, everything that will be poled-like will be in red. Modulo a Galois transformation, I'll explain what I mean, any perp locality evaluator, that I owe you an explanation what perp locality means, but an evaluator with a certain relation here, which I still need to describe. Any evaluator of this type is actually just a minimal subtraction scheme. Namely, I'll go back to this diagram. Remember I said we'll in fact be saying that we'll be identifying a class of evaluators, which is very general. It's a very general class, which in fact, modulo a Galois transformation is a multivariable minimal subtraction scheme. So you see, a minimal subtraction scheme is worthwhile because it's easier. You just have to project. So it's worthwhile finding out how a general evaluator relates to that kind of thing, because then you have less work. So locality on meromorphic germs, independence of meromorphic germs. What kind of germs are we going to look at? It's very similar to Spear, except that we just focus at 0 on germs. So I said everything that's red is pole type, everything that's blue is holomorphic. It's good, we'd like to keep it. And so we're looking at quotients of this type, where everybody, all the LIs, big LIs, small LIs are linear forms. And we'll call L of CK when they depend on K variables. Remember Spear's K variables. we'll put them all in one bag, L of CK. Example, and this is good to meditate on. We want to evaluate this as 0. At Z1 equals Z2 equals 0. How do we do that? So Spear would say, fix Z1 and take Z2 equal to 0. Then you get 1. And then that's all. Now do the opposite and you get -1. If you take the sum of these two evaluations, you get 0. We will not consider his evaluators, and I'll say why later on. The main reason being because they're coordinate dependent. Even if he tried with this action of the symmetric group to make them somewhat independent, but we will adopt a geometric approach, which was triggered by the starting point with Berlin and Vern's approach to cones. So for that, we define not a set, but a space. You see, Spear had sets of variables. We're taking spaces generated by linear forms, everybody on top and everybody below. Remember, he would have said the set Z1, Z2. We take the space generated by the vector E1 minus E2, if we assume we have an orthonormal basis, and the vector E1 plus E2. Okay? So we have these spaces, and then that's why I was telling you perp, our locality relation will be dictated by some inner product. So we have to make a choice. And I'll come back to this. This choice has to, trying to forget about the dependence of Q is asking about the renormalization group. We'll go later to that maybe at the end. So we're saying that two germs are independent if their dependence spaces are orthogonal. You can think of locality. The localities I've met, there are many in maths and physics, I've only met two types essentially, disjointness and orthogonality, because the ones that are separating, so because not all are separating, but the ones, because equality is a symmetric binary relation, but it's not separating. The ones that are separating, I've only met orthogonality and disjointness. Think of, for example, wavefront sets. When you want, you ask for disjointness of wavefront sets, or for when you're wanting to multiply distributions, which is of course related to dealing with divergences, or disjointness of supports of differential operators, things like that. So take Q to be the canonical inner product. So as I said, then this is orthogonal to that because you're viewing this as supported by E1 minus E2, where EI would be an orthonormal basis, and this one E1 plus E2. But of course, if you change the inner product, then this is not true anymore. We'll mostly be working with a canonical inner product, in case I forget to say. So, so Spear, you see, so Spear had this type. I shouldn't have put orthogonal because it's not, it's disjointness. You see, these depend on Z1, Z2, these on Z3, Z4. They're disjoint. So he would say these are independent. And with our canonical inner product, they would also be independent, okay? So his implies ours. So we will have his condition in the background, but we will take a geometric approach. Statement of where we're heading for and ingredients for the proof. I did make a claim. I'm trying to make it more precise as I go along. So we have these meromorphic germs and a locality relation given by this orthogonality of dependent spaces. And with a prescribed type of poles. So you can think of Chen poles coming from typically multi-zeta functions, things like that, Feynman graphs, but I could have trees. Okay. We'll focus on these two, which we now quite understand quite well. Then inside you have the good guys, the ones that are holomorphic, which you can just evaluate at 0. So this is just evaluating them at 0. And this perp induces a splitting. I'll come back to this. This, in fact, was already there in Berlin and Vern's work in 2015 or something. Not quite written in that form, but it is present in many ways in many works on algebraic geometry. Now, we're using this, that's our projection. That's our projection to project naively once we've got the splitting, but it's not easy to get. You have to work to get that. Once we've got this, then we can be very naive. We can just project. And then, having fixed this Q, we're going to try to understand transformations of these meromorphic germs that preserve M plus, the holomorphic part. So we're viewing M dot here as M plus module. And we're going to look at Galois transformations of M as an M plus module. And you'll see why, because that's the theorem we'd like to show. It's the same claim as before, made a little more precise. When Q is the canonical inner product, a locality evaluator, remember that was the one that factorized on orthogonal germs, if you could say it like that. Well, it says here, that is to say a linear form which extends the ordinary evaluation at 0, and 2 factorizes on independent germs, meaning by this orthogonal. Then it is a minimal subtraction composed with an element of this Galois group. So this means this Galois group contains says something about renormalization groups somehow. We don't know what a renormalization group would be here, but it says something like that. Any question? No? Okay, so let's go to locality. I went very fast, and now let me make it a little more systematic. I'll be fast because would be a talk of its own to describe it precisely. But I told you it's a binary symmetric relation. So it's just a subset of the Cartesian product of your set. So you're kind of going from the category of sets to the category of locality sets. And we'll do that for everything. Group, locality group, algebra, locality algebra. When there's a structure on the set, like a group structure or an algebra structure, we need to make sure that the locality relation is compatible. This, you can think of orthogonality. You see, this is the orthogonal set. So it's the polar set. It's all the ones that are independent of a given element. Recently, we realized that if you think of some coproducts which underlie Birkhoff-Hart factorization, you realize that you need a notion of complement. Were it a complement of a subtree of a tree, namely taking the crest of the tree, I don't remember the vocabulary, or were it taking this complement, in inverted commas, of a subdiagram of a diagram, you shrink the diagram to a point and you take what's left over. There's often this notion of leftover of complement. And this notion of complement is essential, I find, for renormalization purposes. Without it, I don't think you can do much. And it was also there in Berlin and Vern's work, because they took the transverse cone to a face of a cone. And this transverse cone was an orthogonal complement type cone. So I told you 2 of them which I've come across are disjointness, and think of disjointness on the power set, or orthogonality on a Euclidean space, for subspaces of a Euclidean space. So we found ourselves trying to make this more systematic, and wrote a paper on locality lattices, and realized that this was in fact quite well known in the lattice community under other names. So we reproved some known results in lattice theory. They call it non-degenerate relations, I think. So locality algebras and modules. I told you we would be looking at the holomorphic germs as the underlying ring for a module. A is here meromorphic germs, it'll be. So we have these holomorphic germs, meromorphic germs, and what will be our setup, we'll have a locality vector space. So any time you put locality with a structure, you have to make sure the structure is compatible, the locality is compatible with the structure. So here the polar set, like the orthogonal to a set is a vector space, the polar set to a set should be a vector space. Okay, and you have to have some compatibility with the product. And the product, remember, Speer defined his products partially, and that's the whole point of what we're doing. We're only allowing ourselves to multiply independent objects, things that are far apart in space-time, if you would like to think of it like that. And we'll be working with algebra A generated by a subset. So this will be meromorphic germs. These will be certain types of fractions corresponding to the poles, but in a locality module construction, namely, you're only allowed to combine a generator with an element of the underlying ring, which is independent of this generator, hence this notation here. Okay, so it might look a bit abstract, and this is summarizing in one slide a whole paper or two papers, so it'll become more concrete, I think, as we go along. Please don't hesitate to ask a question. So that was one ingredient, locality. Second ingredient, Laurent expansion. So it's a multivariable Laurent expansion we have had to work out because we want to project on the holomorphic part in multivariables. So we need a multivariable Laurent expansion. Remember, we had these meromorphic germs, and now we're going to single out the ones that we want to throw away. Remember, we want a multivariable minimal subtraction scheme, so we have to decide how we're going to project, who we're going to throw away. We're going to throw away those which we call polar germs. So S is this. Remember the S of the previous slide, they'll be the generators. You see, these S's will be the generators here, and H, the element, the holomorphic germ of the underlying ring. And let us see what we're going to throw away. We're going to throw away those which are not reducible in a sense, and that is decided by the locality independence, when the numerator has nothing to do with the denominator in the sense that the spaces they generate are orthogonal to each other. We shall declare that this goes to zero. This is polar, pure polar. We don't want to keep it when we evaluate. So these we call polar germs. And they generate a space which depends on Q, because Q is there all the time. And we'll call it, so it's red because that's what we want to throw away. And so Laurent expansions, that cost us a whole paper to develop the notion of Laurent expansion. And for that, we used very strongly the geometry of cones. And so I can't go into it, but the cones are generated by these linear forms. And subdivision of cones corresponds to a decomposition of meromorphic germs into fractions. So you see, in order to have uniqueness, we have to avoid redundancy and avoid cones that overlap. So this is properly positioned. It's in small print because I don't want to go into that. There's another technical condition that the denominators are pairwise non-proportional. Don't worry about all this. The message is we have a decomposition like that, and we could put an orthogonality here. Namely, we can separate F into a holomorphic part and then a dustbin, you could say, which contains all these polar germs. Now, they're not unique. Inside this, there's no uniqueness unless you predetermine what we call supporting cones. So namely, a family of linear forms which are carried or which carry the cones. But this sum is direct, the first one. And this gives you a locality M plus module structure generated by the S's. So I was telling you this, what we put in the bin is not unique. 1 over L1, L2 is equal to 1 over L1, L1 plus L2 plus 1 over L2, L1 plus L2. This is in fact the starting point for the proof. Okay. So third ingredient, the Galois group. So what do? We've got this underlying algebra or ring R, and we've got a filtered algebra, which is R locality module. And we're going to consider morphisms of A, which are linear, such that, they're module morphisms, but locality module morphisms. So we only allow ourselves to couple R and A when they're independent. And we also want them to be algebra morphisms. That's what is said here, but beware that we're only allowing ourselves to multiply independent elements. And the Galois group will consist of such transformations. So TA locality algebra isomorphisms over R meaning that they're module isomorphisms, compatible with the filtration. So you see, T is an element of automorphisms of A, which are compatible with the locality. So that means if two things are local, what does that mean? That means yes, that's right. If A1 and A2 are independent, then T of A1 and T of A2 are independent. They don't have any effect on the underlying ring or algebra, and they're compatible with the filtration. So we'll be very much interested in the case of freely generated locality algebras, namely where this is a basis, S is a basis, because then we can describe an element of the Galois group in terms of the images of the elements of the basis. So that's what we'll focus on. Consequences for meromorphic germs, because all that was a bit abstract. Let's see what we have. So A was our algebra, R was our underlying ring or algebra, and we're in the big setup of multivariable germs, and we've put a locality relation, which is this orthogonality type independence. So with all these ingredients, we are in the setup I just described, namely a locality M plus module. What is a locality evaluator? I did say it vaguely, but now I can say it more precisely. It's an M plus linear form, so it's a form which respects the module structure of A, which is compatible with the filtration, like Spear, that was like Spear, which is partially multiplicative, that was the second condition in Spear. Namely, remember Spear had here independence, disjointness of sets of the variables F and G depended on. Here we have orthogonality, and that's why I was telling you our approach is in a certain sense covariant, because it's a geometric locality. Then we have this factorization over independent elements. So that's when minimal subtraction comes in. We take the projection, because we did everything to have this projection. It was a lot of work, but we managed. And then this then is harmless. Once we're on safe grounds, once we're on M+, we can just evaluate. And as I said, in fact, the beginning of what I'm going to write was already there in Berlin and Vern's work. So that's this decomposition. And it is a consequence of what we did later with this Laurent decomposition, which is much more refined because, oh, there's a typo here, which tells you what this looks like. The Laurent decomposition tells you exactly what that looks like. Once we've got this orthogonal decomposition, we can project onto the holomorphic part without ambiguity. And this is a locality morphism, namely, it does exactly this. When things are independent there, then the pi plus, so what it doesn't say here. Okay, if they're independent there, then they're also independent there. That's important because we want this at the end. So we want this independence not to be spoiled along the way. And since it's not spoiled here, in the end, we will have a locality evaluator because evaluation at 0 is harmless. It does whatever you like. The only thing that could have gone wrong was there, but the whole construction is so made that this locality is preserved. This is thanks to this multivariable setup. We couldn't do it in one variable, not this way. Second consequence, now we're going to work with the canonical inner product. I said that's what mostly we had in mind, but now we have to. And so we're going to work with these Chen and Feynman type poles. And we've shown recently that these are freely generated by polynomial generators, the ones you expected, the ones we had at the beginning of the talk, the ones which were Chen-like and the ones which were Feynman-like. But surprisingly, and that's thanks to Li Guo, who is a number theorist originally, this surprisingly relies on Radford's theorem, which shows that words, the algebra of words with a shuffle product is generated by Linden words. So this is what I write here. So for us, it's very important to know that we have a basis, because then we can characterize our transformations in the Galois group on these generators. We don't need to know them all over. It's sufficient to know them on these generators. So this result was very important for us. And as I said, it goes back to a result by Radford, which says that Linden words are polynomial generators of the shuffle algebra of words. So just again, I think I already said that, but so that you have it still in mind, that's the Galois group, automorphisms of M, which respect locality, which don't touch the holomorphic part, which, yes, that I haven't said, which respect the filtration. You might think, what's the filtration here? I haven't talked about it. The filtration is what we call the p-order. I'm not sure we found the right terminology for that. It's the sum of these SIs, okay? It's the multiplicity of the poles. So this is the filtration. But in fact, the proof uses, well, no, the knowledge, a good knowledge of the Galois group will use more than this. This filtration is just one step. Okay, so final step of the proof. Where do we stand? We stand, remember we started with Spear's, Feynman type meromorphic germs. We added to them the Chen type meromorphic germs, but of course there would be others, trees, but we haven't yet proved this freeness, although we suspect it's true. But for these two, we know that they're freely generated, as as locality algebras. The locality is essential here. We use it in a very essential way. So, because it's freely generated, it's sufficient, that's what I was telling you, to determine, in order to determine an element of the Galois group, it's sufficient to determine it on the generators, TS. That's enough. The rest follows. And this HS is supposed to be independent of S, okay? Because that's all we allowed because of this locality relation. And now, given now the proof, I think that's the proof that's coming up, we take an evaluator, which is a locality evaluator, so it factorizes on orthogonal germs. And we build from it a certain element of the Galois group, which is very simple. We take, so remember it's going to be built on these generators, which are fractions. We take a fraction, send it to itself, plus the evaluated fraction times 1. This defines an element of the Galois group, of the locality Galois group. This is work. This is not that easy because of the locality. There's always work to do for the locality. And once you've defined this, the last line of this slide is trivial because you're evaluating E on S. What does it do on S? You first evaluate T. So yeah, what does it do on S? It kills this because this is a polar germ, so this is killed, and it gives you E of S, okay, which is what you want. That's what it's supposed to do. What does the right-hand side, so that's for the left-hand side, E of S is E of S. On the right-hand side, what does it do? E of S, it sends you here. Now you project pi plus kills everything that's red, so this is killed, and then that's the only thing that remains because this is holomorphic, and then the evaluation just keeps the 1, and so you've got E of S. So the proof, I mean, the last line is trivial once you've got the ingredients. So this says that any locality evaluator is a minimal subtraction scheme modulo a Galois transformation. So there are questions behind the scene, like the dependence on the choice of Q. So Speer chose a certain set of variables. We don't really need to do that, but we do have a choice of Q. And when you choose Q, you can then easily choose an orthonormal basis, etc. So the question is, what happens if you change Q, which means letting the general linear group act? What happens with the evaluators? It's easy to see, they'll be composed. And in fact, we haven't yet shown it precisely, but we've got lots of hints that the Galois group will, in fact, they'll be isomorphic. So it won't change very much. That's if you change, because remember the statement was for the canonical inner product. So of course, we'd like to see what it looks like for another one. And then the next statement is, or the next question, what about beyond orthogonal locality relations, other separating relations? And that's why we wrote this article about separating locality relations, to see what else there was. There are not that many, in fact, but then we'd like to go beyond. And that's more difficult. Well, that's, no, we know how to, we have to redo the Laurent expansion theory for these general separating relations, which is doable. Everything will be doable. It might not be easy to relate these two. So here we don't have Speer's. You see, we started from Speer, but we've left him along the way because his was a set locality. So this evaluator is a good evaluator. It does what Speer wants it to do, but his evaluator doesn't do what we want it to do. His evaluator is too specific. So thank you for your attention. And here are some references. Thank you.
Thank you, Sylvie, for the nice talk. So, are there any question or comment, remarks? Any question?
Did I lose you all along the way?
So, right. So if we don't have questions, additional questions or remark. Okay. So let's thank Sylvie again. Thank you, Sylvie, for the nice talk.
Pleasure. Thank you very much.
And yeah, so everybody stays healthy. And see you next week.